Good morning, everybody. I am rocking a new webcam situation here, so if things go a little awry, let me know somehow in the chat or what have you. Still managing some cables, haven't permanently installed it, but I ordered a official document camera, and it comes with this little clip-on lavalier microphone. So I don't know, it might be cool, might not. It's better than using just a plain old webcam in this application. So today I want to talk about the electric motor and perhaps get to an electric generator, which leads us to a discussion of induction. And short of having a test on circuits and stuff that we should really have soon, if I get this information out to you pre spring break, I think we're really not behind my intended schedule at all. So I'm very excited about this. So the electric motor. How do you build an electric motor? I'm going to draw you a picture here. Basically, you need two magnets or one magnet with a north and a south pole, and I'm just going to draw here the north pole of a magnet, and then over here with a small distance gap away, this will be the south pole of another magnet. And once you have a north pole and a south pole next to each other, you will have a magnetic field popping into existence in the region between. I'm going to draw four representative field lines, but that area will be full of magnetic field lines going from north to south. So what else are you going to put in this region? Well, I'm going to install a loop of wire. Now, this loop of wire is going to be a square loop of wire. I'm basically going to bend something into a spatula shape. As seen from above, it will look like this. And then instead of closing here, I'm going to bring these two out so that you see I've made a spatula. Imagine this is a wire coat hanger that I bent into this shape. There's nothing in the middle. It's not a solid spatula, but it's got kind of a spatula look to it because I've got these things. And what you can do is you can send current to go around this thing in a clockwise or counterclockwise direction. The whole point of this little handle part here is that whatever happens to this loop of wire, it will twist this handle, and that's how I'm going to get my energy out of the motor. So I'm going to draw this shape as seen from above, but I'm going to draw it in perspective in this region between the two poles here. And again, current goes in this way and comes out that way. It's going this way, it's going this way, it's going this way, and it's going that way. Okay, so you can imagine the current going around like this. In this orientation, each of the four sides of this square or rectangular loop of current could possibly feel some force. And we're going to use the right-hand rule to figure out the force. This handle part is out of the magnetic field, so it doesn't feel any kind of force. So let's start by looking at this front edge. The front edge has current going this way, and the magnetic field is going the other way. Now, I cannot get my magnetic field finger to go that way on the page. In fact, if you look at the right-hand rule, the current and magnetic field fingers are at right angles to each other. So this orientation where the current's going one way and the field's going the other way, that's not going to produce any force. So no force on that side. Let's have a look at this other side, the side that's nearest the north pole of the magnet. Now I'm going to put my thumb along with the, actually that should be into the page, right? But I'm going to put my thumb, oh boy, this is hard, really hard. I guess, there we go. Okay. So putting my thumb into the page, because this is kind of representing into the page, and my index finger pointing this way, you can see that my force finger points down. So there is going to be a force downwards on that side. Now I know there's a lot of arrows in this drawing, but we'll do another version of it that might be a little easier. On the back side, the alignment between the current and the magnetic field, they're aligned together. There's no angle, so there's going to be no force because we don't have anything to work on. On this side, the current is coming out of the page at you. The magnetic field is this way on the page, so the force is upwards. See this? Upwards. So this side of the thing is going to be lifted upwards. If we were to draw this in a more simple way, we would look at it from the edge, and we would see that the magnetic field was like this, and that the currents of interest were going into the page over here and coming out of the page over there. And then you can do this a little better. Into the page, magnetic field forces down, out of the page, magnetic field forces up. So this side's pulled down, this side's pulled up. And that is the way that we get energy or torque out of an electric motor. So this magnetic field, when the current shows up, will try to twist this thing. And eventually the little spatula shape will move to where it is. And let's go over here. Now I'm back to a perspective drawing, so maybe I should include let's go down here. Perspective drawing, we're going to include the faces of the magnets. South, north, and a little representative magnetic field in the area between them. And now this thing will twist a quarter of a turn until it's in this orientation. That is to say, the right-hand side will finally be at the top, and the left-hand side over here will finally be at the bottom. And the forces will now be pulling up and down, and the net torque, the twisting motion of the motor, will stop. So that seems like I built a really lame motor. I put the thing in, I hit the juice on the current, and it turns a quarter of a turn. And this is where things get clever. If you want this motor to continue working, what you need to do is you need to turn off the current at this point. Let the motor coast until it goes a little further, maybe even all the way to this orientation again, and then turn the current on in the reverse direction. Because remember, this current was going this way over here. Okay, I'm sorry. This current was going this way, and it has now become the one on the top. When we get this thing to roll over and get on this side, we need the current going the other way. So the trick in a motor is to turn the current on one way, let it rotate a quarter of a turn, turn the current off, and then reverse it as soon as you get past vertical, and then it flips around to the other vertical. So what you're doing is you're alternating the current a number of times every second. And that is the genius of alternating current. That's what Tesla realized, is that motors need alternating current in order to continue spinning in a circle. Now, what about a generator? I said something about a generator. Well, as you know in life, many times, if something works one way, it also works in reverse. In this case, for the motor, we had a magnetic field, we added current, and we got motion. But a generator uses the same pieces, and we have a magnetic field. We are going to add, had magnetic field, I turned it into hab. I'm going to leave that. That's great. I haven't had my coffee yet. We're going to add motion. Lord have mercy. And we're going to get current. That is to say, we are going to take, for our generator, our north-south magnetic field zone here. And we are going to stick a loop of current, or a loop of wire in there. And we are going to spin it around. And when we spin it around, what we're going to do is we're going to generate current. Current's going to come out of there that didn't exist before. This is current that doesn't come from a battery, and it doesn't come from a capacitor, and it doesn't come from, let's see, what else makes electrical current? A buildup of static electric charge. This is called magnetic induction. This current and the voltage associated with it was referred to as EMF by the people who are researching this. This technique is the way that we make most of our electricity today. We use magnetic induction. We put coils of wire in a magnetic field and we spin them, usually by boiling some water and forcing steam through a turbine to make something spin. And what comes out is alternating current. Now, a couple things I want to say. The fact that a motor can be turned into a generator is in evidence today in modern electric cars. In modern electric cars, when you're not actually trying to make the car go faster, a lot of times the electric motors turn into generators, steal energy away from your forward motion, and turn it back into electricity and put it back in the battery. This is referred to as regenerative braking. One of the hardest things that people had to get used to when the Tesla automobile first came out is that the gas pedal on the car, you press it down, you go forward. People are used to that. In an internal combustion engine car, when you lift off the pedal, you kind of coast, right? Well, in a Tesla, when you lifted off the pedal, the car would actively slow down because it was regenerating electricity back into the battery from the motors acting as generators. And so there was a way of driving it, and people refer to it as one-foot driving, where you didn't lift your foot all the way off the gas to coast. You had to lift it to a certain spot on the pedal, and that was the coasting spot. And then if you lifted more, the car would slow down. I have the same thing on my Chevy Bolt. It's actually enableable. If you put the car in drive mode, then when you lift off the pedal, it just coasts like a regular internal combustion engine car. This is what most people are used to. But if you put it in regen mode, then when you lift off the pedal, it does a moderate amount of slowing down. Not like slamming on the brakes. Let's be honest about it. It's just moderate slowdown. Actually, the car, when you do the moderate slowdown, will light up the brake lights because it doesn't want you to get hit from behind by somebody who doesn't know how these cars work. But it's a fantastic way to keep your battery topped off. Also, I believe in the Tesla and for sure in the Bolt, there is a little switch behind the steering wheel, and when I squeeze that switch, I get extra regenerative braking. So I can drive in slow and go driving. I can do that without touching the brake pedal in my Bolt, and I'm constantly putting energy back into the battery. So it's one of the ways that they extend the range of these cars. Also, these big, heavy, permanent magnets that I've drawn here to create the magnetic field, this is impractical to put in a vehicle. I suppose you could do it for a land-based generator, but the permanent magnets don't generate very large magnetic fields. So in reality, these two will be replaced with coils, with solenoids. So if I was going to draw a picture of a modern generator, I would draw a solenoid on this side, a solenoid on this side, and then in between them would be this magnetic field, and I would put my coil of wire. And let's just draw the flat spatula shape that I drew before, okay? So there would be current going through here at all times to generate a magnetic field, and current going through here that's alternating in order to produce the rotation. And you know, if you look at this, this is just in one dimension. This is one flat plane. Why can't you have many of these coils? Like, let's do another set that's up here and down here, and another coil of wire that's separate from the first coil, but it's at another angle. Oh my God, I'm going to draw this. It's going to be so horrible. Okay? And indeed, modern motors have many sets of these solenoids, which are known as field coils. And many sets of the other coils, which are sometimes referred to as an armature. And they have torque all the time, and various parts are being energized at various times to create very efficient motion. So I know this drawing is ridiculous and absurd, but this is what you get from me this week. My artistic skills have gone downhill for some reason. Let's talk about this magnetic induction for a second. So when you have magnetic induction, the amount of EMF that you get, which is equal to a voltage, is equal to the number of turns of wire, 1, 2, 5, 6, or whatever, times the change in the magnetic field times the area over time. In other words, changing the magnetic field or changing the area, twisting the thing. This is the induction formula. So if you want to generate voltage or EMF or even current, you need a number of turns of wire. The more turns of wire, the better. You need a magnetic field. The stronger, the better. And you need an area that these turns of wire have in their center. So for my spatula shape, the area in the center was this area right here. And there has to be some sort of change in either the magnetic field or the area. And changing the area is the most common thing to do. And I can kind of demonstrate that Here's a little card that I got from well, I need something smaller. Okay, here we go. This is smaller. There's a little set of Post-it notes. Now I'm going to turn off the lights here in this room. Ah, okay, it didn't turn off the lights in the room. My dimmer switch is broken. Nice. So now I'm using one single light source, and so if we imagine the flow of light from this light source as magnetic field, you can see based on the size of the shadow here that I am intercepting quite a bit of light. I have quite a bit of magnetic field going through here. But when I twist the card, the area of the card, you can see it, it's shrinking, it's getting smaller. And pretty soon, now this is straight at the camera, so this is the minimum area to the camera, but my light source is a little further ahead. If I keep twisting, when the card is edge on to the light source, then you see that I have the minimum amount of light intercepted. So maximum light intercepted, or in my analogy, maximum magnetic field intercepted, minimum magnetic field intercepted. So that's why twisting is such a great idea. It does make a huge change in the magnetic field times area. This, by the way, this magnetic field times area is known as magnetic flux. So if you ever hear the term flux, well, actually, the term flux just means flow in Latin. I'm going to show you some demonstrations in class next that are going to have something to do with generators and motors and induction. The last thing I want to say, induction. No, I'm going to save it. Electromagnetic waves. We're going to save that. So this is the lecture on how an electric motor works. I'm going to try to link some additional videos with better graphics for you, and off we go.